Right, good afternoon everyone. Thank you very much for coming along to Efficient R Programming. So my name's Colin Gillespie, and today we're going to be looking at Efficient R Programming. The term's quite loaded, so I sent around a pre-course questionnaire to get a feel for part of the audience, and I'll describe sort of the general makeup of the audience and then tell you how I'm going to proceed through the next few hours. There's a course package, and I'll update this package after the tutorial and fix any typos that we find. I'll also add solutions to the exercises. What I found is that people in general just cheat, and so if I give you questions and there's solutions, you'll just look at the solutions. So I'll add the solutions afterwards. And this is how to install the package. So you need to do the first two lines in order to get the package. Okay, so the first line is installing a package called Drat. And Drat's a very cool, tiny little package created by Dirk. And essentially it allows you to create your own repository. Okay, so on GitHub, there's a repository just filled with my packages, so for use for teaching. The second line, this add repo, adds another URL. So when you do install.packages, it finds somewhere else to look. And then the third line installs this package. So the package efficient tutorial isn't actually on CRAN, it's not on Bioconductor, it's sitting somewhere in GitHub, and those two lines above just allow you to access that URL in a nice, simple way. So if you've not got that done, don't worry, I'll put that slide back up. But all the course slides are in the package, some additional exercises as well. And when we come on to the exercises, I'll stick that back on so you can do it. Right, so who am I? So my name's Colin Gillespie. I'm a senior stats lecturer, so associate professor at Newcastle Uni. So I do lots of the usual things that academics do, teach undergraduates, PhD students, research interests. I quite like Bayesian computation, a bit of experimental design. Would you believe messing about in computation? You know, parallel computing, cloud computing. I am also a consultant at this company, Jumping Rivers. So that's a data science company based, would you believe, in Newcastle as well. And basically we do lots of fun things. So we do mainly statistical and R consultancy. We do lots of training in R, Scala, Python, Stan, predictive analytics, in-house training. We like to believe that we have the most unique swag ever. So I've brought along coasters, so no other company I think of in data science has their own coasters. So there's 50 coasters down here. Please take them, because I really don't want to cart them back in the plane. They weigh a ton. And if you take one, I can guarantee you that in 5 years' time they'll be worth absolutely nothing. But you have the privilege of remembering today. So there's only a few. They come from fake wood. Well, there is a slight bit of wood there. To a luminous, lost in the dark orange and yellow. So feel free to grab one. And I've been kicked off Wi-Fi. Right. So sorry, I'm going to start with an apology, which is never a good way of starting off a 3-hour tutorial. My voice seems to be going, so I blame small children. Small children are the bane of my life, in particular my own. When my children have been sick, I just sent them to school last week and told them to stop whinging. Now I've got the same thing that they had. I'm whinging, and I'm a bit worried that midway through this next 3 hours, my voice will die. So what I've done in the last few hours is I've reduced the talking time part and increased the hands-on part. And I realised that that's not great for a large room in a tutorial, and it's not perfect, but it was either that or I might just my voice will give up. So apologies now. Also apologies if you hear me blowing my nose. I don't think mute works, so I'm just, all round sorry for everything, but it's children, not me. Right, so who are you? And time to make a friend. So what I mean by that is we're going to be doing some hands-on exercises, and it's quite intimidating when you come to a conference of this size. There's hundreds of people. You might never have met anyone at all, and you might be just a bit embarrassed to talk to the person next to you. So what I'd like to do for the next 2 minutes is make a friend. Now, a friend, it doesn't count if you know the person next to you. You need to make another friend, right? So you have to increase your friend count by 1. So for the next 2 minutes, find someone who you've never spoken to, or you might have forgotten the name, which is just a bit embarrassing, and see where they're from and what wonderful things they can do. Right, so 2 minutes, and then we'll get back. But time to make a friend. Right, hopefully you've now made a friend for life. So one of the nice, my voice is going. One of the nice things about the R conference, I've been going for a few years, is it's actually one of the most friendly conferences. So I go to quite a lot as an academic. Sometimes things are a bit cliquey, but the R conference is actually quite good fun, which is why I try to come every year. So yeah, try and talk to someone else. I might force you to make another friend later on. So before the course, I sent around a questionnaire, and we had about 60 responses. I think there are more than 60 people in the room. So these are asked people, what type of person are you? What was interesting is people are moving from statistician to data scientist. So the data scientist is definitely the future. We have one manager in the room, so who identified themselves as a manager. I won't ask you to identify yourself. There was a free text box, and someone put in transitioning physicist, which I found quite amusing. I won't ask you to identify yourself if you're a transitioning physicist. I'm not sure if that means you're I can't even say that word. If you're coming from physics to something else, or you're going to physics, we'll leave that one. I had a little question to try and gauge the underlying R ability. So I asked you about, on a scale of 1 to 10, how easy or hard would it be to write a function? So 1 would be very easy, no problem at all. 10 would be pretty tricky. So most people in the room are fine with functions. Not everyone, but most. And in loops, something similar. So for the most part today, I'm assuming that that's pretty much done. Okay, so I'm not going to explain what a function or for loop is. We're just going to assume that that's done. Around about 40% of people have built a package in the room, and most people haven't used C and C++. Okay? So we're not really going to be talking about packages, but when we come on to RCPP, Duck did a tutorial this morning, and so I was on that similar tutorial years ago, and it's great, but it's quite intensive. Whereas when we go into RCPP, it's assuming that you're coming from a non-programming background and have never used C. Okay, so it's very basic, very fundamental. Today's tutorial's a subset of a course that we run, Efficient R Programming. It's also a subset of a book that we published last year. The whole book's online. Okay, so it's just search for Efficient R C.S. Gillespie, and all the slides are in the tutorial. I strongly suspect that not everyone's going to be able to install the package. Okay, just Wi-Fi issues. Don't worry if you can't install the package. We can get through that. You can do it afterwards and get a copy of the slides, so it's not a big deal. Okay. So, what we won't cover, we're not going to cover RCPP in depth, right? So when we come on to RCPP, which will be the last thing, we're going to cover on what's C, how to run a bit of C code, very much a basic introduction, right? We're not going to cover dplyr and friends, right? They're wonderful, but there's lots of other talks, there's tutorials on dplyr and friends. We're not going to talk about joys of Git, or the terror of Git. I don't know about you, but if you ever use Git in the command line, it's like a different language. So the joys of Git and reproducible research. Not going to talk about pipes. We're not really going to talk about big data either. We're not going to do any stats whatsoever, except for the mean. So we're not going to cover any of that. What are we going to do? We're going to look at a bit about byte compiling. Okay, so have a brief talk about byte compiling. We're going to talk about low-hanging targets. So it's not so much stuff that makes your code go faster. It's more things that you really shouldn't do to make your code go slow. Right? So it's not more a bonus, it's just things to avoid. We're going to look a little bit about code profiling, and then test the waters of parallel computing in RCPP. And similar with parallel computing, the idea is to give you a flavor. Right? So what I hope at the end of today's 3-hour tutorial is that we'll do the parallel computing part, and you'll think, yes, I want to go and learn more about that, or no, it's a complete waste of time. And even if it's the latter, spending half an hour to discover that you don't need it, or it's not suitable, is quite useful. And the same with RCPP. We've spent half an hour, and hopefully at the end of that half hour, you're at a stage where you can think, yes, I want to go away and use it, or no, I don't, and here are the reasons. Okay? Especially if you've got a boss who just picks up buzzwords like cloud computing and parallel computing and multi-core. So having a rough idea of what's suitable is the idea for today's tutorial. So, optimization. So this was a quote by Don Knuth. So he gave a talk last year at the useR conference in Stanford. It's one of these people that's just incredibly clever, and whenever you think yourself quite bright, you look at people like this and you think, wow. So he's a Stanford computing science professor, and he's so good that he doesn't need email, which I just think is amazing. So it's wonderful. And this is quite a nice quote. Premature optimization is the root of all evil. Right? Or at least in programming. And what I think is happening here is don't worry too much about optimization in day one. Right? We'll cover bits and pieces of stuff to avoid, but don't spend all your time and all your effort caring about optimizing to the nth degree right as you start. Take a step back and think, do you need to worry about optimizing? When we go into parallel computing and when we go into RCPP, these are things that will make your code go faster. But typically there's a downside, right? So with RCPP, the downside is you need to learn C or C++, which is, shall we say, a bit on the tricky side. Right? The downside about parallel computing is, well, there's going to be thread communication between your cores, and in some cases it will make your code go faster, in some cases it will make your code go slower, but there's a downside. Okay? So don't worry about this stuff too much until you really need to. So we'll just start by thinking about timing code. We'll start basic. And there's two simple ways of timing code. There's this function system.time, and then there's a function called microbenchmark that's in the microbenchmark package. Okay? So system.time comes with R, and microbenchmark is a separate package that pretty much just does that one thing. It's just for timing functions. So system.time. So here on this bit of R code, what we're doing is we're generating a whole bunch of random numbers. What's that, 10 million random numbers from the normal distribution. And then we're raising it to the power 2.3. I have no idea why I chose 2.3. And then we get some timings out of it. And we get three numbers, okay? And we've got user, system, and elapsed. And essentially the number that we care about with system.time is elapsed. Okay, that's sort of the total time it took to run the bit of code. The system time is essentially the internal sort of computer messing about, just sort of thinking about what it's doing. So typically the system will be close to 0, so perhaps 0.0001, right? And hand wavy, usually user plus system equals elapsed, okay? So as long as the user is sufficiently, it's a bit bigger than system, you just stick with elapsed. That's nice and easy. So this is quite good, right? So we can run a bit of code, and it tells us our time. Notice I've used the arrow operator, right? And it's quite strange or quite odd to use the arrow operator inside a function call, right? So if you think to all the function calls you do, you don't tend to put the arrow there. You tend to use equals, right? You might use arrow for assignment, but you wouldn't really do it inside a function. And this is the sort of the key difference between arrow and equals here. So here, object x not found, okay? And if I had something like mean of x 1 to 10, I've got 5.5. That seems correct. But object x is still not found. If I do the same bit of code and change it to the arrow, then still get the same answer, but x is now magically been created, okay? So when you use the arrow operator, it does two things inside the function call. It does the argument passing part, right? You're getting this value 1 to 10, you're passing it to the function, but it's also doing the assignment in the scope that it was called, okay? Whereas equals is only doing either assignment or argument passing. It doesn't do both, okay? So I quite often do this sort of stuff where you've got a bit of code, and you're not quite sure how long it takes, so you want to run the code when you leave the office at night, but you also want to have a rough idea of how long it took, and not come in the morning, say it took 2 hours, and think, right, I need to run it again. So it's quite a handy little trick of figuring out how long something took and storing the result. So it's quite nice. The trouble with this is it's hard to compare multiple benchmarks. It's not really hard, right? You can do a for loop if you wanted, or you can copy and paste. So it's not, it's not that hard. It's just more of a pain. And the micro benchmark package just makes this easy, okay? And so here I've loaded the package microbenchmark, and we've got an example where we're comparing a matrix and a data frame. Okay? So I've got a matrix, and I've called that DM, and I've got a data frame, and I've called that D_DF. And what I'm wanting to do is compare the time to take a column or take a row from a matrix and a data frame. Okay? So is there any difference? So both the matrix and the data frame are the same size, otherwise that's just cheating, and they contain exactly the same data, but the class is different. Right? So they're both just big tables of numbers. Right? But the matrix is a matrix, and the data frame has got a class data frame. And if you look through all these numbers, well, so we call the microbenchmark package, we've got an argument called times. So that means that we're going to call each of these functions 1,000 times. Right? And microbenchmark is actually quite clever. And it's not going to do the first function, then the second one, then the third one. It's going to do them in a random order, right, in case there's anything nasty going on under the hood. Okay? We can specify the units. So here I'm specifying milliseconds. If you don't give that argument, it just defaults to something sensible. And then I've got the list of functions I'm wanting to call. So I've got D_M, brackets 1. So that's selecting the first row from a matrix. Then the next one is I'm selecting the first row from a data frame. Then the third one, selecting the first column from a matrix. And the fourth one, D_DF, 1, selecting the first column from a data frame. And you get back out a whole bunch of stuff. Okay? And the key thing to notice here is if you look at the main column in that table, right? So we've got min, median, mean. If you look at the column mean, you notice that all the numbers are more or less the same except for the second row. Right? So they're all sort of, decimal, second, third decimal place, except for the second row. Okay? And that's when we're selecting a row from a data frame. Right? So selecting columns is more or less the same. Right? Matrices are slightly faster, but if you're worried about that sort of speed up, don't be using R. Selecting a row in a matrix is roughly the same as selecting a column, but selecting a row in a data frame is a real pain in the rear end. It's it's orders of magnitude slower. Right? And so the interesting question is not that the interesting part is not that selecting a row is slow, it's why is selecting a row slow. Right? So whenever you're doing these timing operations and you come up with an answer, if you can try and ask or understand why, then that's when you start picking up things and that's when you start learning. And also, even if you couldn't figure out for the life of you what on earth is going on here, right? You might think, right, I've no idea. You've now got a nice question for Stack Overflow. And I know that Stack Overflow people are evil and they'll eat you alive. It's all lies, mostly. But that's a nice question of, I've got some code, I've ran the code, I've got two things, one's slow, one's fast. Can someone help explain why one's slow and one's fast? That's quite a nice question. You've got reproducible code that you can ask. Right? And they might close the question and point you somewhere else, but it's quite nice. So, why is it slow? Well, what I'm going to do is I'm going to pause, because, actually I just need to cough a little bit, but the real reason is you can then talk to your newfound friend and see if you can come up with a reason of why selecting a row from a data frame is a bit slow. Okay, so I'll give you 30 seconds, 1 minute, and then we'll come back. Right, we'll go on to the next part. So, why is a data frame so slow for doing a row? Well, a matrix and data frames are quite similar, right? They're both tables of stuff. But a matrix, all the stuff must be the same, right? So it must all be numbers, or all logicals, or all characters, right? So you can get a character matrix, and that's fine. Whereas a data frame, that's the thing that we use all the time for statistics, the columns must be the same, but two columns can have different types. So column 1 could be ages, column 2 could be address. Okay? So you've got a column of numbers and a column of characters. So what does this matter? Well, if you imagine you've got a matrix and you know how much, the type of each value, so it's quite easy thing to store. Right? You just imagine your hard drive, a big long vector, a big long array of all the elements in your matrix. It's all in one part because it all takes the same size. With a data frame, each column could be different sizes. Right? So you've got columns scattered all over your hard drive because a column of characters is longer than takes more memory than a column of numbers. Okay? So the overhead here is actually when we have to find all these different bits scattered about. You've also got an additional overhead because a data frame is just a more complex object, it's got a lot of baggage going along with it. You know, a matrix is just a table of stuff. A data frame has got lots of other bits and pieces hiding behind. Right? It's actually a list of vectors. Okay? So essentially, you know, the reason why we use data frames is because we have different column types, but that comes with a penalty. And now, what I'm suggesting is not that we all run out and start using matrices, because, well, real data is a pain in the rear end, and it's probably not all going to be numbers, but it's just to be aware of the differences, right? And sometimes these things can help. This micro benchmark package has also got a plot function, okay? So res was just the output of this thing here, and so if you do plot res, you get a nice little box plot of the 4 results. And that thing there, that's selecting a row from a data frame. The one on the far right-hand side is selecting a column. Right? So you can see that selecting a row or a column in a matrix is more or less the same. Right? One's slightly faster than the other, but you know, we're not talking much. Selecting a row on the far right-hand plot of selecting a column on a data frame is fast, but not as fast as a matrix, because you've got a bit of overhead. But selecting a row, well, that's a bit more painful. So, use our resolution. Never ask a question in Stack Overflow which method is faster. Right? So if you ever do Stack Overflow, whenever you see a question saying, you know, I've got method 1 and method 2, which one is faster? That's the sort of thing you can answer yourself. Right? You've got micro benchmark, you've got system.time. So if you ask a question in Stack Overflow, it should never be which one is faster. It should be why is A faster than B? Right? That's a sensible question. Right? So it's easy to time these things. Right, on to byte compiling. Right, so the byte compiler. So the compiler package has been part of R since 2013. Okay, so that's what, 6 years ago. It turns out there's many institutions in the UK that are still doing R12, which is just scary because they tend to involve lots of money. But there you go. So the compiler package has been around since 2013, and it does magic. You know, that's the best way of describing it. You know, it translates R functions into another language that can be interpreted faster. Right? It just does magic under the hood. So I just like to think of this as a magic thing. And essentially what happens, since 2014, so again, sort of 5 years ago, all the standard functions and packages in R will be precompiled. So that's base, the core recommended packages and recommended packages that come with R have been compiled. What does that mean? Well, if we look at the function definition of mean, right? So here I've got said, get me the function definition of mean. So I've got the arguments in line 1. Okay, so it's taken in an argument x, and it's taken in 3 dots. It's what we call an S3 method, S3 generic. Line 2, the use method. That's this funny S3 object-oriented stuff. Don't need to worry about that. Line 3, the bytecode, right? So that's saying that this package has become compiled, right? So on the previous slide, all standard functions and packages in R will be pre-compiled. So if you look at any function that comes with base R, you'll have that second last line saying bytecode, right? And then some sort of hex number after it, okay? So, right? So this is the lm function, and second last line, bytecode, okay? If I write a function called f, and look at the function definition of that, there's no bytecode, okay? So all the standard functions that come with R have been byte compiled. Right? So it's been happening without you even knowing it. And R 3.4, so that was the one that was out just 2 months ago. It's got something called just-in-time compilation has been enabled, and we'll come on to that in a second. Right? So I'll explain what I mean by that in a second. Right? So from this slide, we've got something called the compiler package that everyone's got on their machine, unless they're on 2.12, in which case, why? All base R functions come already pre-compiled, and compiling a function essentially allows a speed boost for free. Right? That's the sort of the take-home message here from this slide. So, the base R functions are compiled, so if they can do it, why can't we? Right? And actually, is it worth it in the first place? Right? Is it just a waste of time and effort? So, here's a function. This is called bad mean, right? So this is a function for calculating the mean. And it's bad. It's correct in the sense of it will give you the right answer most of the time. But you shouldn't do it this way because you should use the function mean, right? That was written by clever people, optimized. So we've got standard R function, or standard way of calculating the mean. We've got the function definition, so it's going to take in an argument x, and that's just going to be an argument, a bunch of numbers, a vector. We've got a tracker variable, total. It's going to keep track. We've got n. It's going to be the length of the vector. So we'll pass it some numbers, work out the length. And then we've got a simple for loop that just goes through each element in turn and calculates the running total of the mean. Right. As I said, bad mean. Don't copy. Okay? So, how do we compile it? So we can compile this function using this CMP fun function. Right? So it's part of the compiler package. Right? And if you look at the definition now, so we've got CMP underscore mean underscore R, and we're compiling a standard function. We've now got that magical phrase bytecode at the bottom. Right? So we've now got a bytecode version. Okay? But since 3.4, this is now done automatically. Right? So if you're using 3.3, 3.2, 3.1, you would have to do this step, or some variation of it. There's other ways of doing it. If you're using 3.4, it's done for you automatically. So when you're writing R code, when you're scripting, it's going to do that sort of compiling step for you. This just-in-time, right? JIT. So it's just-in-time compilation. Okay? And here, one does not simply time R code. What do I mean by that? Well, here I'm timing how long it takes to calculate the mean. Right? So I've generated some random numbers from the normal distribution. So in line 1, we've got 10 to the 7 random numbers. And then in line 2, we're using system.time. So we're trying to figure out how much time this function call is taking. And we've got mean underscore R, the mean underscore R of x. And then when we do it again, we get something slightly different. Right? So if you notice up here, the user number has changed. Right? You've got a bit of a change in the user number. Right? Essentially, we've got this just-in-time compilation. So the first time we run it, it's a little bit slower while it does that compiling step, but then afterwards, it's on its way. You only need to compile once. So when you're compiling functions, there's a tiny little overhead to start with, but it's a one-off cost, and it's next to nothing. So these are the benchmarks from R 3.4. Right? So here I'm comparing the mean function, the compiled version of mean, and then the super duper R version of mean. Okay? I'm doing each of these functions 10 times, and the units are going to be in milliseconds. And would you believe it, the mean function is a lot faster. Well, who'd have guessed? But what's better is the compiled version is a lot faster than the uncompiled version. Right? And the compiling step is pretty quick. We're talking less than, not noticeable typically. Okay? And if you do a little plot, so in the x-axis we've got sample size, so that's the size of the vector going into my function, and it's ranging from 1,000 to, 100,000? So as we move from left to right on the x-axis, the size of the vector is getting bigger. The function mean, would you believe, is always the fastest? Well, that's written in heavily optimized C code. Right? The function, the compiled version of mean, is gradually getting slower. This is relative timings. So here it's round about 25 times slower than the C version. But that's a lot better than the uncompiled version, which is 200 times slower. Right? So compiling functions does have a good potential of speeding up your code, with essentially little to no overhead. Now, as I said, 3.4, it does this magic for you, right? So it just compiles it just in time and everybody's happy. And you think, well, if that's the case, why on earth are you waffling on about this? Well, it compiles your code, but it doesn't compile packages, okay? So you've got your script, you're running your script, that stuff's compiled. But you've got some packages out there that you've downloaded and installed, and they're not necessarily compiled. Right? Some are, some aren't. But the vast majority aren't. So if you're a package author, then you can stick this line in your description file. So as package authors in the audience, you can stick this option in your description file, byte compiled to be true. Okay? And that's pretty much it. So one of the packages I developed is on power laws. So it's quite a computational thing. There's lots of Monte Carlo simulation, lots of for loops. And adding that one line gave a speed up of around about 4 to 5 times in some of the main functions for users. All right? So package author, stick it on. You might want to do a few tests just to make sure bad things don't happen, but I've yet to find bad things. So that's if you're a package author, what you can do. If you're a user, this is what I mean. Only around about 3% of our packages are byte compiled. Okay, so this line of code here is just grabbing the CRAN package database, and then we're grabbing the byte compile flag, and we're working out a percentage. So only 3 to 4% of packages are byte compiled by default. But we can make packages we install byte compilable, if that's the word. Right. So you can add this flag r_compile_packages to your .r environment file. Okay. So what's this file if you're not familiar with it? Well, when R starts, it looks for 2 files. It looks for your R profile, and it looks for this file here. Your R profile, you tend to put in helpful bits of R code to get your session started. And there's lots of nice optimizations you can put in there to make your day-to-day life nicer. In this file here, you'd put in system variables, right? So the sorts of things that you'd put in here would be where to find your R libraries, for example. System variables, not R code. Or this thing here, r_compile_packages equals 3. Right? When you're compiling a package, there's 3 levels, 1, 2, and 3. If you're going to go for it, you might as well just go full hog. Right? So why bother with 1 and 2 when you can go for 3? So you just need to add that line in. And what that will do is when you now install a package, it will automatically byte compile the package when you're installing it. And now the obvious question is, if it's all so easy, what's the downside? So far, there's not many downsides. So I've been doing this for maybe 2 to 3 years of just byte compiling everything. And I think I've probably got 1,000 packages in my system. I just install all sorts of random garbage from the internet. The downsides are, it can take a bit more space, the zip file under Windows. But since you're all probably sitting there with a terabyte laptop with absolutely nothing on it, then it's not a big deal, is it? It can take a bit more time to install. Well, we're talking an extra few seconds as opposed to an extra 10 minutes. So again, not a big deal. The only time I found it really annoying is if I'm developing a package and I'm doing a clean refresh and I'm constantly installing it, then it's installing 10 packages at once, and I'm just a bit lazy and don't like waiting. But really, that's about it. You can also install it from the command line. So here, install.packages ggplot2. If you're a Windows user, you need to use it from source, and that usually means you need RTools if it's got any C++ code. All right? So if you're a Windows user and you want to do this, you're fine for pure R code, but if the package contains any C code or Fortran code, then you need RTools, which is a bit of a beast to get on. Okay? So, yeah, so it's, as I said, I've been using this for a few years now, and I do it routinely with everything. It just seems to make things go faster. The other downside is, especially if we go through Stack Overflow, the question is, well, why isn't this done automatically? So it's only relatively recently that this stuff has been particularly stable. So if you search Stack Overflow, there are old questions where someone's byte compiled a particular function and it's gone 10 times slower. So that was sort of R3.1, I think was the last time. But now it seems to be pretty much stable. And I think there's an odd thing that can happen with a browser function with byte compiling, but again, that's more of an edge case than a day-to-day case. Right. Any questions? I can't see anyone at all, but does anyone have any questions? Yes. No. No. Yeah. So the nice thing is, your code is exactly the same in the sense of you've not done something special. It just runs a bit faster. The worst that can happen is it doesn't run faster, but I've not found a situation where it runs slower. So, okay, didn't gain anything. Well, Life sucks, but there you go. Yep. I'm always wary of answering these questions when there's members of our core kicking about. I think since they've put in just in time for R3.4, the obvious next step is yes. That would be the obvious thing. But our core are conservative and doesn't like breaking things, which is a good thing. So, anything else? Right, the next part is we're going to be doing some common pitfalls. And now, during this session, I'm going to get you to do some typing. I know I promised at the start to make it more hands-on, but the byte compiling part, there wasn't really much to make you do hands-on. So, the benefit of using R is that coding time is greatly reduced, right? You know, while you can read in a CSV file, do some regression, create a scatter plot, your C programmer is probably Googling Stack Overflow of how to read in a CSV file. Python, not so bad, but still it's just not as good as R. Right? You know, we use R because we can get stats up and running with some nice plots with a couple of lines of code. So our coding time is reduced. Right? You know, we're saving our time. And our time tends to be quite expensive. But it's really easy to write programs that are slow. So this part, these next few slides, isn't so much about efficient programming or how to make code go faster. It's more about don't do this. Right? This is just bad. Okay? And again, I apologize. You know, we've got a large room of 100, 200 people, and it's hard to try and pitch this. So again, some people might find this basic, and I apologize, but it's just trying to get something for everyone. So object growth. Right? So method one. Here we're going to create a vector and then grow an object. Right? So line 1, we've set n to be, 100,000. And line 2, we're creating a vector myvec. Okay? Both of these calls in line 2 do the same thing, or fundamentally the same thing. Right? They're both creating an empty object or an empty vector. Right? And then in line 3 and 4, we've got a for loop that is just going to grow this vector. So let's see what happens. Right, so when you run that bit of code, you come up with a vector 1, 2, 3, 4. Right? But the crucial part of this code here is you're starting off with an object of size nothing, and then at each iteration you're adding on a bit at the end. Okay? So you started off in line 2 with nothing. So here, myvec is nothing. And then when you run the for loop, you've gradually grown the vector. Right? So the length of the vector is changing during the for loop. That's fine. Method 2 is it's more or less the same. Hate doing live demos. Right, it does exactly the same, but on line 6 of the console, when I run this thing here, what's happening is I'm creating a vector filled with zeros, and I'm going to be filling it in. Okay? So the first one, we're starting off with nothing at all, and then we're gradually growing it. The second one, we're starting off with something, and then we're filling in the blanks. Okay? And then the third one, just for completeness, is that. With the length I'll get eventually. Okay. So I'll do the same thing. Is there any difference? So that's object method 2, method 3. So, here's some timings, right? So n is the size of the vector, the size of the for loop. So we're going 10 to 5, 10 to 6, 10 to 7. Method 1 is where we're growing the for loop, or where we're growing the vector, so things are getting larger and larger and larger. Method 2 is where we created the object to start with, and then fill it in the blanks. And then method 3 is just the sensible way of doing it. Okay? And these timings are in seconds. Okay? So we've got 3,827 seconds, which is about an hour. Right? So you've got 3 bits of our code. One takes an hour, and one's going so fast that we can't actually time it. Right? So that's what I mean of, it's not so much efficient, it's just don't do this, this is bad, evil. Right? The middle one here, it's not too bad, 2 seconds. But this one here is sort of the difference between code that works and code that really doesn't work. Right? So if you're doing any sort of loops, just check your length before and after. You know, it's a simple check. And you can see these are timings. So the y-axis is the log scale in seconds. We've got method, that should be method 1, that should be method 2. So the bad method's this thing here, and it's just linearly increasing with the vector length. Okay, so as r increases, as the size of the sample increases, this thing slows down. Right? So don't grow your vector, really bad. Sometimes people don't tend to do something quite so obvious. Right? So here's a little bit of code. And it's simulating a biased coin. Right? You can tell I teach undergraduate statistics. So simulating a biased coin, and we're selecting a number at random, so simulating a random number between 0 and 1. If it's less than 0.3, then we're going to say it's true, it's a hit. If it's bigger than 0.3, we're going to say false. All right? And the crucial thing is, this vector hit starts off with size nothing and then gradually grows. It's bigger and bigger and bigger. And that's bad. Evil, in fact. And this is where I get to get a break, because you good folk get to have a little shot trying to rewrite this into something a bit more sensible. Okay, so I'll give you a couple of minutes. Feel free to talk to your newfound friend. Right? You might want to judge whether your friend's competent and get a new friend for the next part, but I'll leave that up to you. It's not a judgment thing. Rewrite this to something a bit more sensible. And we'll come back in 2 or 3 minutes. Good? Right, so all that really required was a change in line 2. Right? So the idea of, the easy check is look at the size of the objects before the for loop, look at the size of the objects after the for loop. Okay? That's how we do it. If you want to be really cool and clever, then you can write it in one line, okay, which is vectorized code. So line 11 does exactly the same as all the stuff up above. Okay? So lots of our functions, we'll come on to this in a second, are vectorized. So rather than generating one random number after another, well, why not generate them all in a oneer? Okay? So R makes this trade-off all the time of essentially memory and speed. Right? You might think, well, we don't want to generate n things because that's going to take up memory. But R does this all the time of vectorized computation, generating big objects and then using them one after another. So that's what to be honest, it's just my bad habit of, so I would change it to, I'll just change the type. I really should have made it a logical or used vector and mode logical at the start. I would just have the bad habit of using numeric to start all things. So if you really want it to be proper, rather than having numeric n, you could use a vector function and specify that you've got mode logic, and that would be slightly nicer. Yeah, well, I do because I put it in line 1, so I know the size of my for loop. Right, another common thing is rbind does the same. Okay, so what you can quite easily do is you've got a bunch of CSV files and you stick them on a little for loop and then you whack them together using rbind. So rbind short for row bind, so you've got data frame 1 and then data frame 2, then data frame 3, then data frame 4. Okay, and so it's quite easy. You have something like this. So you create an empty data frame, or the data frame might come from reading in an initial file, for example, and then you've got a for loop, like the one in line 2, and that might be a loop over CSV files, for example, or database tables, or something like that. And then you've got some sort of R-bind where you're taking your data frame and then sticking something on at the bottom. Right? And that's doing the same growing. Right? It's just the same as before. Right? You've got a data frame of 10 rows, and then it's going to be 20 rows, then 30 rows, then 40 rows, then 50 rows, then 60 rows. It's getting bigger. So you've got the same fundamental problem. Right? So here what I should do is generate enough space at the start. Okay? It makes your for loop all sorts of a bit more messy, but that's the correct way of doing it. You generate your data frame this size, and then you fill in the blanks, and that's quite nice and efficient. Okay? And often when you're reading in lots of files, you might not know how many rows you need in total, but you've probably got a good idea. Right? If you're Bayesian, you'll have a prior on it, so that's fine. The do? Oh, do call. I think that suffers from the same thing, does it not? Yes. Sorry, nope. Got what you mean now. Yes, no, that's the other way of doing it. So rather than sticking it all in a data frame and doing R-bind, you can create a list at the start, put in each element in the list, and then do call in R-bind. And yeah, that's better as well. But essentially, growing things is bad. Growing lists is okay. It's just a sort of different type of data. You don't have that problem. But data frames and vectors, bad. So, first rule of R Club is never grow a vector. I'm not quite sure how to make this a thing, but yeah, if you all tweet it, then we might get it going. So the first rule of R Club is never grow a vector. I'll just leave that picture and go on. Moving on swiftly. So vectorizing. So again, if you're familiar with R, I apologize. This is all quite standard. Here's some R code, and what we're doing here, so in line 1, we're generating a bunch of uniform random numbers. We're adding on 1. And then on line 3 and 4, we've got this vectorized code where we're calculating the log sum. Okay? So you're taking log of the first element, then log of the second element, log of the third element, log of the fourth element, and adding them all together. And this is quite C-like. If you're a C program, this seems how you would do it. My first language was something called Fortran 77, which is an abomination. But it's sort of, it's a very good bit of Fortran code or C code. It's that sort of nice stepping through. But in terms of R code, it's not the best. Right? And here, we're not growing a vector. Log sum, this object log sum is only going to be a scalar. It's only going to be a single value. But we're growing this thing. We're not growing this thing. But we're doing the repeated calculations. And what we wanted to do is to go down vectorization. And so the better way of doing it is to do something like that. So you've got your vector x, which is a bunch of numbers. You're then taking logs of all those numbers. You're then taking the sum. Right? So that's about 40 times faster. It's neater. And it doesn't contain a dodgy bucket of length 0. Right? Because a bit here, we've got length of x. What happens if the length of x is 0? Right? Bad things happen. You don't get an error. You just don't get the right answer. Okay? So vectorizing is another thing you should think about. The trouble with vectorizing is these toy examples are quite sort of obvious. And then when it comes to actually real-life problems, it's just a bit more tricky. I don't know if you find that, but it's easy sort of having toy examples of course you should do that. But then you come to your own example, and it's just a bit more tricky. But again, most R functions have this vectorized idea. So a vectorized idea might be it takes in multiple arguments or multiple values and returns 1, like mean. Or it might be like the random number generators where it takes in a value and returns a vector. Right, so there's lots of vectorized arguments. So, I need another break. So spend the next maybe 2 or 3 minutes and you can rewrite that in a more suitable format of vectorized. So, simple little for loop, and we're just selecting values of x that are less than 0. Okay, so here we're going through this vector x, I've just chosen length x to be 10, and we've got an if statement, and we're just selecting all the values that are less than 0. What's the best way of doing this? So I'll give you 1 or 2 minutes, and then we'll move on. Right, so all we needed is the sort of standard subsetting stuff. What I've found, especially when you look through R code, especially packages, that sort of stuff is quite common, especially, it's not so much that someone's a bad programmer. There could be a great programmer in another language, and they're just coming over to R. Okay? So it does crop up more than you would expect, and it's just not great. So, one last example. Monte Carlo integration. So I quite like Monte Carlo integration. If you can remember back to your school days, that's integral sign. So x squared is a function, and it's a happy face one. So you get the happy face, that's x squared, and you get the sad face, that's negative x squared. So we've got x squared, which is a happy face, and we're trying to find the area under the curve between 0 and 1. Right? So picture a graph going from 0 to 1 on the x-axis, 0 to 1 on the y-axis, with happy face. And that's said happy face there, that curve there. That's x squared. And what we're wanting to do is we're wanting to estimate the area under this curve by Monte Carlo integration. So Monte Carlo is just a posh way of saying there's some randomness going on. Right? So we're talking about Monte Carlo integration. And what we're going to do is we're going to close our eyes, and we're going to throw a bunch of darts at the board, and we're going to count the number of darts that fall below this line. Okay? And the way of thinking about how this works, if you're interested, is imagine you've got a line going across at 0.5, right? So rather than the one we've got, imagine you've got a horizontal line at 0.5, and you throw 1,000 points at the board. How many of them would you expect to go below 0.5? Well, around about 500. So you could estimate the area of 500 over 1,000. Imagine you had a horizontal line at 0.2, and you threw 1,000 darts at the board. How many points would go below 0.2? Around about 200-ish. So that gives you an error. So it turns out that whatever the line is, so here we've got nice x squared, if we just throw lots and lots of darts, count the ones that fall below, we can estimate the area under the curve. So it's quite nice. So this is the algorithm, and this tends to be the way that algorithms are written in scientific papers. Right? So we've got initialize hits as 0, and then we've got for I in 1 to n. Okay, so we're going to throw n darts, so capital N darts. We might throw 100 or 1,000 or 1,000,000. Right? And then we're going to generate 2 random numbers between 0 and 1, u1 and u2, and we're going to use that to find my coordinate. Right? So what I'm wanting to do is I'm wanting to simulate throwing a dart at this board. So if you were to simulate throwing a dart at this board, you'd want to simulate a value in the x-axis, so it's a value between 0 and 1, and a value in the y-axis, another value between 0 and 1. So that's a u1 and u2 is my dart position. And then on the second bullet point here, we've got, did the value fall below the curve or above the curve? Okay? So u1 squared, what's u1 squared? Well, u1 is my x-coordinate, so u1 squared would give me the value of that dark blue line. Okay? And so we're just counting the number of points that fall below the curve. Okay? Monte Carlo simulation. And then we can estimate the area, so the number of hits over n. And this would be a standard way of writing an algorithm, very much procedural. We've got a nice for loop. This is what we do. And you could rewrite this in R, and, well, if it was me, I would just copy the algorithm to try and reproduce the results in the paper or the tutorial, whatever. And so we've got a little function called f, and we've initialized in line 3, hits is 0. And then we've got that for loop going from 1 to capital N, where capital N is the number of darts. And we're generating 2 random numbers, u1 and u2. That's going to be my dart location, right, my xy coordinate. We've got a little if statement. The if statement is going to tell, are we above or below? And if we're below, we're going to keep track. Okay? So it's sort of, you've got your algorithm, you rewrite it as R code. All right? That's what I'll do. And you can time it, and it takes round about 1.8 seconds. So it's pretty fast. Can you think you can vectorize this code? All right? So I'll give you a minute to do it. I have to put my hand up. So I taught this stuff to first years. It was about 5 years ago. And I didn't spot for about 2 years that this could be vectorized. So if you don't get it, it's not a big deal. But how would you vectorize that code? Right. So give you 60 seconds just to have a little think and see if you can think of, can you do it in one line? Just as a matter of interest, how many people think they've got a one-line solution? I'm not going to make you come up and do it. Well, probably not. Okay, that's quite good. So, essentially, n's the number of darts. Go away. And so we can do the comparison if you can type. And that. So let's make that a bit smaller. So n's 3, we can generate the one coordinate in one go. We can generate the other coordinate and square it in one go. And thank you. That would have been 5 minutes of my life wasted. Yep, and then we can vectorize that, and then we can just work out the mean. Normally you'd want a sample size bigger than 3, typically. So, yeah. So, second rule of our club, vectorize when possible. I can't think of a third rule, so any third rules, please email or tweet. Last little bit. So, again, sometimes you can't vectorize, you're not growing. What can you do? And again, this last part is sort of, I think, obvious is the wrong word, but second nature to people from a programming background. Right? So here we've got a few functions and some code. So what's going on here? So this is what we call a particle filter in statistics, or a very noddy version of a particle filter in statistics. And what we've got is we've got a function in line 1 called jitter, and what the function jitter does is it's going to wiggle points. So I'm going to give it a number, and it's going to give it a little wiggle. Okay? And then in line 2, we're creating some 10 values. So that's my particles, right? So it's my sort of initial conditions. And then in line 3, the post is where we're going to put the result, right? So we've got some particles, we've got some 10 random numbers, we're going to wiggle them all, and then we're going to stick them in this vector post, right? We're not growing a vector because we know that's bad. And so we've got this for loop here. And so we've got a loop from 1 to the length of particles. We calculate k, so k is going to be how much of the wiggle that we're going to do. So it's this bizarre number of 1.06 times the standard deviation of the parts divided by the length of the parts. Can't remember where that comes from. I think it's, if you start assuming normality in infinite dimensions, it all falls out. But it's a standard way of sort of keeping your particles alive. And then in the last line of the for loop, we've got this jitter function. And what it's doing is it's going to take in each value and then give it a little wiggle and give it a wiggle according to this parameter k. Okay? So that's a particle filter. You've got 10 points going through, and then you wiggle them each in turn. And that bit of code can't really be vectorized particularly easy. Right? But there is one trivial thing you can do. Right? One really easy thing you can do. And that's if you look at line 2, we've got k is 1.06 times the standard deviation of parts times divided by the length. That's a constant. Right? So the really obvious thing to do here is just take that one line out your for loop. Right? So rather than calculating the standard deviation 10 times, calculating the length 10 times and times it by 1.06, you take it out. Typically, the number of particles in these things is 1 million or 10 million. It's a big sweep. Right? So again, if you're doing loops or anything like that, can you cache your variables? Right? So something that you can calculate once and reuse. Right? And, it's a sort of a simple thing, but yeah, just take it out. So, this was there's some exercise in the package. I'll put how to install the package up. There's 8 minutes to coffee. I don't want to suggest you don't need to do the exercises. The exercises try to take in sort of different examples in what we've covered, right? So it's not just the same stuff. The examples in the tutorial, in this vignette, are reading in data sets, so comparing read.csv, read_CSV, RDS, fread from data table. So is there any differences? What's the drawbacks? Also There's one on data frames and matrices, a slightly different twist again. So we've got 7 minutes to do that. You're not going to do it in 7 minutes. But when we come back after coffee, we'll go on to parallel computing. So I'll stick up how to install the package again, and then you can do the tutorial. Personally, what I would do is I would run and grab a coffee before everybody else is finished, and then come back and do the tutorial, have a shot of the questions. Okay? So I'm happy to be, well, I'm going to be here. I'm just going to grab a coffee and then come back for any questions. We'll start again in 37 minutes, and we'll go on to parallel computing, followed by a bit of C++ for the remainder of the tutorial. So going up a level, getting a bit more tricky, and that's how to install the package. And if you browse the vignettes for the package, you'll see the questions for this section. Okay, so they're called common. Okay, and we'll start again in 36 minutes and 50 seconds according to this counter. Please take a coaster, because I really don't want to take them all home because they're heavy.